Welcome to my YouTube channel. Right, so what we want to discuss is the mathematical representation of wave motion. Now, the first thing is, let's draw the wave motion. Okay, so let me just use this and y displacement along the vertical line and then time in seconds. Alright, we have amplitude here, and everything I'm drawing here is just one wavelength. Okay? Now, if you look at this diagram very well, you discover that this graph is a sine graph. So it means that y equal a, which is the amplitude, sine theta. Mathematically, we know that theta, or from simple harmonic motion, we know that theta equal angular speed times time. Let me just do a quick revision and treat the similarity between simple harmonic motion or circular motion with normal velocity, like when something is moving on a horizontal plane. Alright. So we know that the horizontal is velocity equal distance over time. But in the case of simple harmonic motion or circular motion, we're not using the velocity, we're using angular velocity, which we use omega to represent it. And we're not talking about x position or distance, we're talking about something circular, and that's what we're going to be using theta over time. So that's why theta equal wt. Okay, having said that, so it means this equation equal a sine wt. And we also know from simple harmonic motion that our angular speed w is equal to 2 pi f. So it means that this equation can be written as a sine 2 pi f. So I'm going to title this as equation 1. Let's assume that this is not starting from the origin. Let's assume that it has started over some period of time before it begins. So let's say the diagram is like this, and then okay. So this is the time in seconds, and this is the y in meters. Alright, let's say it has started over some period of time. So, period of time, how do we get that time? Watch. We know that v is equal to x over t. So, therefore, time is equal to x over v. So, let's say it has moved a period of x over v. Somebody will be asking, why am I using time? It's because this horizontal line is time. Do you get it? Okay, so if it has moved this certain time, see, if it has moved this certain time, it means this equation now will now be y equal, remember everything is this, and then we are taking away this from this. So it will equal a sine 2 pi f. Now this is time for everything. Right, so we write t minus, what is this? This everything here is time. That's why you have to put it like this. So I'm going to write x over v. Alright, so but we know that v, which is the speed, is f lambda, right? So I'm going to put it, alright, y equal a sine 2 pi f. We will write t minus x over f lambda. If I open the bracket, I will have a sine 2 pi f t minus 2 pi f x over f lambda. So this, we cancel this. Now y equal a sine 2 pi ft minus 2 pi x over lambda. So now this is the mathematical expression for wave when it begins after a certain period of time. Let's say it begins before. So I'm going to have a graph like this. Let's say this. Okay. And this is the time in seconds. This is my y in meter. And everything here is the wavelength. Alright. We are looking at this. We looked at after a period of time, the waves started oscillating. Let's say we've started before the origin. So what will it be? It's just the same thing. This has moved a distance of x over b. Right? So now the expression for this will just be exactly like this. But what we're going to be having will be y equal a sine 2 pi f t plus 2 pi x over lambda. So it means now that the general formula now is y equal a sine 2 pi f t plus or minus 2 pi x over lambda. So now this is the general mathematical expression for wave motion. Now let me have one thing. Let's say this is not time. Let's say this distance. What will it become? So I'm going to play this. I'm going to put x, the displacement, and meter. So what will the expression be? Now it's just the same thing, but I'll be cleaning something. All right. Now we don't want time now. We want to do it in respect to x. So how do I do that? We know that velocity is equal to distance over time, right? And we know that v is f lambda equal to x over t. Alright, so I want to take away this. So if I take it away, it's going to give me, and let's look at this, f lambda t equal x. We want to talk about these two guys. So I'm going to take over lambda, so I'm going to have ft equal x over lambda. So it means this equation will now be x over lambda. Alright, having said that, and we're talking about what will this one be? Because we're taking this away and then we are putting meter here. Sorry, putting x displacement, which is meter. Okay, and let's talk about this. We want to look at position. We want to look at the displacement. So this time around, I'll make it x sort of formula. So x equal vt. So everything here now be vt. So now the equation now will now be y equal a sine 2 pi over lambda, because I just want to talk about x, which is this. But now it has started after the origin. Now it has moved a distance of minus vt. Alright? So let me open the bracket. So our a sine, let me just put this into the bracket. Our 2 pi x over lambda minus 2 pi bt. Now we know that b is f lambda, right? We know that b is f lambda. So if I put in, okay, I forgot to put lambda in, right? Because 2 pi x over lambda minus 2 pi bt over lambda. So it's now going to give me a sine 2 pi x over lambda minus 2 pi, I'm taking v away, I'm putting f lambda c over lambda. Lambda cancels lambda. So we're going to have y equal a sine 2 pi x over lambda minus 2 pi ft. So now this is the general equation when we're talking about the displacement, the horizontal displacement. So these are all the formulas we need, this and this, to solve some questions. Okay, so now in the next video, I'm going to write down some questions and then we're going to solve it. Thank you.